say that one more time.
I'm trying to find delta E over delta X. What is the slope of my electric field versus position graph?
This might be completely wrong. The amplitude.
Oh, you stopped me there?
Yeah.
No, there's more. I was hoping you would do more.
Oh.
What's the slope of the sine graph?
Or the, oh yeah.
It'd be the
Cosine.
I think you poured it out in the middle of your sentence, so you want to go ahead and take credit?
I don't care.
All right, so the slope of the sine graph is cosine. And then I got kx minus omega t. But then something else pops out front. K. Just the coefficient of x. Equals negative. All right, now we're doing b with respect to time.
Is it Bm omega cosine, or omega, yeah, omega cosine kx minus wt?
One small tweak. What is the coefficient of time?
Angular frequency. Or
More than that.
seconds.
You said seconds?
Yeah.
Coefficient of radian.
No, just looking at the formula right there. What's in front of the t?
Omega. T. Oh no. Negative omega?
Negative.
So does that make it the whole thing positive?
Yes, it does. So I end up with b sub m omega cosine kx minus omega t. Now, if we're making the claim that the left and the right hand side are always equal to each other, that can only work if the coefficients are equal. So the maximum electric field, or the amplitude of my electric field times the wave number, has to be equal to the magnitude of amplitude of my magnetic field times the angular frequency. So the speed of my wave, as we discussed last time and earlier today, is omega over k, and that would be equal to E sub m over B sub m. So whatever my amplitudes are, the speed of this electromagnetic wave is just the amplitude of my electric field divided by the magnitude, amplitude of my magnetic field.
Wait, it's just wave speed, right?
Pardon?
Wave speed?
Yeah.
This is chapter 24 stuff, right?
Yes. All right. We're halfway there. Because we used Faraday-Lentz's law, we haven't used Ampere's law yet.
Okay.
And go. All right, so what we're going to do for Ampere's law is I've got my electric field going up and down, my magnetic field going outwards. All I'm going to do is I'm going to take a look at this, except I'm going to tilt it back like this and look at it from that point of view. So magnetic field is up, the electric field is going into the board, because we're now going to look at it from sort of looking that way.
Oh, I see what you're saying.
So taking this, so I have the magnetic field going this way.
You might want to use the black.
Yeah. The magnetic field going like that. And my electric field going away from us in a beautifully rendered three-dimensional drawing. So as I look at my Amperian loop, or whatever you want to call it, I'm going to take a little segment right here. And I know that I need some more. There's my loop with a width of delta x and a height of L. My electric field is going into the board. Oops, sorry, that's out of the board. My electric field is going into the board. And my magnetic field, well, for the magnetic field, I know here, magnetic field is B, and here it is B plus some change. I picked a spot where it's increasing as I go. Now, I could have picked a spot where it's decreasing. I could still put plus delta x where delta x is negative, but it's just easier visually for me to do it this way. Since my electric field is going into the board, I'm going to do my loop going clockwise against the right-hand rule. My thumb points in the direction of the electric field.
That works for electric field too.
Yeah. So I'm going to start here, and then I'm going to move up. There's my A, B, C, and D. Now there is no actual conventional current running through my loop here. So this part of my equation is 0. So I'm left with the sum around this loop, B dot delta L. Before Jack complains about my handwriting.
Sorry, I can't read.
Excellent, I'm not. Delta phi sub B over delta D. And so now we're going to do the exact same process we did before. Is I'm going to start with my side A there, and I have B times L. Along B, my magnetic field and my length vector are perpendicular to each other, so dot product is 0. Along C, B plus delta x is going up. The length is going down as I'm going around this loop, and so it's minus B plus delta x times L. Yes?
Why is the equation there different from the one over there?
Okay, it's just this piece right here missing. Because this is the conventional current, this is charges moving through it, but I don't have any charges moving through this. Any charges involved in the problem would be over here in the creation of the electromagnetic wave.
Okay. Thank you.
Yep.
So if we find that there are no charges, we can leave that part of the equation out?
Yes, in essence, it's plus 0. For those who like it, 0 plus. And then along segment D, well, my length vector is to the right, or left, as people say today, and my magnetic field is up. They're perpendicular, so the dot product is 0, and that's going to be equal to mu sub naught, epsilon sub naught, change in E dot A over delta D. And again, I'm going to make my area vector to be in the direction of my electric field. So this becomes mu naught epsilon sub naught. My area vector is constant, delta E over delta T. And on the left-hand side, I have BL minus BL minus B delta X, distributing. And so I end up with negative B delta X. When I started the process, I wasn't thinking it would actually make noise, other than the clanking. But apparently, someone sent something to the printer and didn't bother checking.
And we get to look at what they printed.
Chemistry practice problems. Sorry to have defiled this class with the mention of that. All right, so now, same process as before. This is negative B delta X equals, oh, that's B,
Piece of that.
nope. I lost something here. Oh, God. Where's the stupid mistake I made?
Did you?
The L off the delta,
The L off the delta?
or it was BL minus L delta X.
Okay, that's one mistake. What's the other mistake I made? I should have done plural. What are the two stupid mistakes I made? Think units? Would that help? See, this is the influence of inferior subjects. Even though I made the mistake before I walked over and knew it, the presence was there. That should not be an X. That's a delta B.
Oh,
That. What that would be, yeah.
well, that changes things.
Minus L delta B. So I have negative L delta B.
Yeah, this is the best we started. That's so much better.
Yeah, you know.
And you're old, so.
I know. It's only gonna get worse. All right. My area, what's the area of my rectangle over there?
L delta X.
So this is equal to mu naught, epsilon sub naught, L delta X times delta E over delta T. Conveniently, L disappears. Sure. And I'm going to divide both sides by delta X, so I have negative delta B over delta X equals u naught, epsilon sub naught, delta E over delta T. And we're going to go about to do some slopes. Questions up to here before we slope?
I'm sorry, is that a delta X on the left side of the equation?
Yes, that's a delta X on the bottom.
So, the magnetic field with respect to position is the same as U sub naught, delta E over delta T.
Yep.
And what is that top part of the delta, like, what's up with the mu sub naught, epsilon sub naught, delta E represents the electric field?
E represents the electric field. This is the permeability and permittivity of free space. mu sub naught is how a medium is affected by a magnetic field, or it's a quantification of that. Epsilon is a quantification of how the electric field affects the medium.
Okay.
So negative delta B, now it gives me the number, of delta x is equal to mu sub naught, epsilon sub naught, delta E over delta T. All right, so what is the slope of the magnetic field with respect to position?
BM cosine K or BMK cosine. Then Kx minus omega t.
All right, and then on the right-hand side, how does the electric field change with respect to time?
EM omega cosine kx minus delta t.
Is it negative omega t?
Yeah, it's negative omega.
Oh, I forgot some bits.
Which is convenient, so the minus signs will cancel out. Matter of fact, let's cancel out that which we can. The cosine goes away. Well, officially, the coefficients must be equal. This is always equal. The minus sign disappears. And we are left with the amplitude of the magnetic field times the wave number is equal to mu naught, epsilon sub naught, E sub m omega. I know that the speed of this electromagnetic wave is equal to omega over k. From this equation here, that means I'm bringing k over to the left, and I'm taking this all over to the right, so I get b sub m over mu sub naught, epsilon sub naught, times the electric field. Sub m. And that is equal to what we did the first time. That's equal to the magnitude of my electric field over the magnitude of my magnetic field. Amplitude, you'd say magnitude, amplitude. Doing a little fancy work here, I'm going to multiply both sides by the electric field divided by the magnetic field. So I'm going to take this and multiply by E sub m over B sub m. And on the left-hand side, I get 1 over mu sub naught, epsilon sub naught. And on the right-hand side, I get E sub m squared over B sub m squared.
Why can you multiply them by that? By E sub m over B sub m?
Well, I'm multiplying both sides by it.
Oh,
So math people say that's okay.
yeah.
But again, if the math people lied to us, well, everything we've done in this class is wrong, potentially.
They're really good at lying.
That could be. But so far, buildings aren't collapsing, so I'm trusting some of what they've told us. So I know that the speed of this wave is equal to E sub m over B sub m, because that's what I got over there. So that's just the square root of this. If I take the square root of both sides, I get the speed and then that. So I get the square root of 1 over mu sub naught, epsilon sub naught. Well, let's do a little plug and chug. So first off, I think Maxwell did this, as opposed to someone later on, but we'll represent the speed of this electromagnetic wave by the letter C. C represents the speed of an electromagnetic wave. And so he is claiming that the speed of this wave is square root of 1 over 4 pi times 10 to the negative 7th Tesla meters per ampere times epsilon sub naught, which is 8.85 times 10 to the negative 12th. And let me break that for Jack. Actually, we'll write it down here. 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared. And we end up with
Oh boy. That's a big number. $299,863,380.
units.
That's a speed, meters per second. Meters per second.
What are the chances? Nope.
So, the square root of 1 over mu sub naught, epsilon sub naught, all of that over meters is also a second. Or no? Wait.
So, if we're gonna do it that way, then, let's see, we have square root of ampere Newton meters squared per Tesla meter Coulomb squared. It's equal to a meter per second.
Yeah, that checks out with me.
So Tesla meter Coulomb squared, and then, yeah,
Obviously.
yeah, obviously. So a second, therefore, would be a meter times square root of Tesla meter Coulomb squared per ampere meter squared. Or the square root of Tesla meter Coulomb squared per ampere Newton.
Yep.
Now, some people might claim that using seconds is simpler, but, you know, it's not as pompous.